All right, so we left off about using this binomial distribution. Right? So we said the setup was we see either a success or a failure, right? Or a binary outcome. We see something occur, we don't. We then have some underlying probability of success on any one of these experiments, right? We're running the experiment n number of times, right? But every single time we run it, we have the same probability of seeing that success or seeing that failure. And then the third thing that we needed was, well, we're basically using this binomial function, right? That looks a little bit nasty to talk about factorial. That's going to give us the probability of seeing a different number of successes out of whatever our n number of trials is, right? So X here is going to be the thing that's kind of changing in every single problem, right? We could actually, for the same kind of setup, here I'm choosing 5 people at random was the example we left off on. And I'm trying to see how many of them have a college degree. Well, I know that if I select any one person at random, the probability they have a college degree is 0.3, right? So I might want to say, okay, what's the probability that see, there's X, we'll put the probability of X being equal to different values on the y-axis. So we want to find the probability that 0 of the 5 people have a college degree. We want to find the probability that 1 people out of the 5 have a college degree, 2 out of the 5, 3 out of the 5, 4 out of the 5, and then all 5 out of the 5. So I think I kind of showed you at the very end of last class, like if we wanted the probability of all successes, right? Some things simplified for us a little bit. We found the probability of 3. Now, I don't think we worked it out how we found the probability of 4, but we said that what should be true is whatever the mean or whatever the expected number of successes was, which we said was just the number of trials times the probability of success. So for us, just to kind of recall from that example, was 1.5. So we said that 1 and 2 would be the most likely outcomes, right? Now I have to plug in X is equal to 1 into this function, solve it to get the actual number for what those probabilities would be. But we know before we even calculate them, they'll be the 2 most likely outcomes. From there, we know that the probability of seeing a higher number of successes or a lower number of successes as we move in either direction from this mean, right? Those probabilities have to be declining. And I think this is intuitive if you think of like a coin flip example, right? If I flip a coin 10 times, more often than not, 5 of them are going to come up heads. But, there's a relatively high probability. Maybe I get 6 out of 10 or 4 out of 10. But then what about seeing 7 out of the 10 come up heads? That's less likely. Well, what about 8 out of 10? It's quite a bit less likely. 9 out of 10, until you get to 10 out of 10, very, very unlikely. So as you move away from this kind of expected value, this mean, we should see the probabilities decline. Okay? That's kind of where we left off. Okay. So go one step further with this, which is what if I wanted to know the probability that at least 3 out of the 5 will have a college degree? Okay. So at least 3 out of 5 is really saying what's the probability X is greater than or equal to 3. Okay. Well, because we're dealing with a discrete random variable, we can only see integer values. What are the only outcomes that I could see that would fit that criteria? 3, 4, and 5. And we said last class, I can only ever see exactly 3 people, or I see exactly 4 out of the 5, right? I can't have 3 and 4 out of the 5 have a college degree, right? It doesn't make any sense. And so there's no overlap. These are mutually exclusive events. So if we want to find the intersection, right? The intersection. If we want to find the union of these 2 events, the probability of 3, or the probability of 4, or the probability of 5, we have nothing we're double counting. We said when we have mutually exclusive events, we don't have to worry about subtracting out the intersection. It simply becomes adding up the probability. So just a reminder there. If I'm looking for the union of 2 events, and I'll get out of the way in a second, and they're mutually exclusive, I can just add up the probability of each event. So here, I can find the probability X is equal to 3, plus the probability X is equal to 4, plus the probability X is equal to 5. Now, that means I'll have to use that binomial equation 3 different times, n will always be the same. The underlying p probability of success will always be the same. It's just that the number of successes I'm finding the probability of, or x, I'll have to update. Well, we've already done this, right, for 2 of them, right? If we go back, I think, yeah, 0.13, and I think if I go out to the third decimal, it was 0.132. And then we found the probability it was 4.028. And I think I even showed you last class that what we plug in 5 here, we want all the successes, a bunch of stuff simplified. Remember, everything really, if I've got x and n being the same, all these 4s would be 5s. The only thing we were left with is actually what's in the middle here, 0.3 to the 5th. I don't know what it is off the top of my head. I know it's probably going to be something really small, right? I mean, think about it, the probabilities are declining as we move further away from this mean. Well, the probability was equal to 4 was 0.028. And just notice going from 3 to 4, how much the probability fell. We want the probability all 5. I mean, I'm guessing it's approximately 0, right? We could go ahead and compute this. In fact, I'll show you in Excel, use it as my kind of calculator here. I'll zoom in. Oops. So we can actually see what I'm doing. But right, one thing that we showed last class is it really just simplifies down to what we had in the middle there, which now you can't see. I'll smooth this over. All right, that simplified down to really just what was in the middle for that 0.3 is a bit. So if we do that 0.002, okay, it's not quite as small as I thought it might be, but still out to the third decimal pretty small. All right, now I add those all up, and that gives me the probability x is greater than or equal to 3. Okay. Oh, no. Any questions on that? So before I just kind of ignore the second line for a second, but any questions kind of on kind of that idea of just adding the probability of every outcome basically that just fits what you're looking for, right? Now we have to be careful, right, with our equality. So what if I said, what's the probability more than 3 people have a college degree? Now what would I do? Actually easier, because I'd only have to do 1. Yeah, I actually only have to use that binomial equation 2 times. Because the very first outcome I could see that's greater than 3 for a discrete random variable would be the value of 4. Okay. Questions on that before we keep moving here? Okay. All right, so actually I think, so here's the, we add these up, we can already have these values on there, but it's, you get under these in your calculator, you get 0.162, right? So I want to show you a couple things about some statistics for a binomial variable, and then I'll return to, there's also something else that we might want to introduce before we kind of move on to Poisson distribution. So we said the mean is kind of this intuitive thing, but there's an actual formula for it, right? If I know the underlying probability, if I select someone at random, they have blue eyes, is 0.15. Out of 100 people, the most common number of people I'll see have blue eyes is 15, right? Now it's easy to think about that when I have 100 people, because it's like probability of 0.15, oh, it's 15 out of 100, right? When we have different numbers, I don't know, 63 and 0.24, right? It's a little bit harder to visualize, so we might want to actually have this formula, which is all we're really doing there is taking the number of trials, multiplying by the probability of success on any one trial. Okay? Now the variance isn't quite as intuitive, but it will always follow this equation. Right? So you can imagine what we're actually doing here to give a little bit of an insight without going through the entire proof. What did we say? The general form to find this mean was we took every single possible x value, multiply it by the probability saw that value, right? To find the mean of a discrete random variable, like before we even were talking about binomials, just like a general kind of discrete random variable. Well, here I've got my different outcomes I could see for x. So I could think about, I could then take every value for x minus the mean, square it, then add them all up. Well, these are just binomial functions, so I can plug in the binomial function there. It's a how, it's a messy equation, but there is an equation. We could write this out. And what ends up happening is you write that out and you have, a bunch of n's and p's and x's here. It'll actually always simplify down to this equation right here. Yeah.
We don't worry about like sample population and all this.
No, we're not dealing with data anymore, right? We're trying to make projections for the future. So this is going to be some future outcome. Yeah, so we don't have to worry about sample population stuff when we're dealing with random variables. Yeah. At least for right now. In practice, it'll basically always be samples, right? Because, well, we just need to understand the basics of these discrete and then continuous random variables. And then we'll talk about how we introduce sampling into that. So I guess technically, if you want to think about it, all populated for right now. But we will eventually introduce the idea of what happens if we're doing some sampling of the population. But yeah, this is population stuff. It's a good question. Any other questions? Keep going here. How would I find the standard deviation? That's pretty easy, right? I just take the square root of the variance. Okay. So, it's pretty easy to calculate these two things. I think I got a problem here, but honestly, I'm not gonna. We could do this. It's just plugging the values in, right? We already talked about what's the mean of this random variable for the number of people that have a college degree. Well, n times p, 5 times 0.3 was 1.5. How will I find the variance? Well, notice it's actually the mean times 1 minus p, right? Or n times p times 1 minus p. So we would take 1.5, multiply it by 1 minus 0.3 or 0.7, right? These should be pretty easy calculations, I think. You'll have these formulas on the formula sheet. So if I ask you for the mean and variance of a binomial variable, these should be easy points in the exam. Probably giving you that to make sure that you get the easy points out for that question, right? Now, the only thing you have to be careful of is if I ask for the standard deviation, you'd have to remember you have one more step, which is take the square root. Okay. I generally don't pull things out of the book, but I like some of their stuff. So I like this visual because I think it kind of also gives a good, I don't know, it kind of lets you think about, okay, we could have a ton of different binomial distributed variables, right? Because n, the number of trials, even if I'm flipping a coin, I could change that from anywhere from 1 to, well, not 1, anywhere from 2 to, I don't know, the infinite, right? As many times as I can flip the coin in my lifetime, right? I can also play around with the probability of success, right? Depends on the example that I'm talking about. Okay? So for different combinations of n and p, what would these distributions look like? Okay? So notice if I had something pretty small, kind of n here, it's just 5. This is kind of like our college degree example. Probability of success relatively low, 0.1. Well, if our probability of success is relatively low, right? We're always going to be more likely to see lower outcomes, right? This would be the idea if there was a probability of something happening of, 0.01. Well, if I run this experiment 10 times, the most likely outcome I'm probably going to see is that 0 out of the 10 are successes. Right? Now, as that probability increases, well, yeah, now 0 is still the most likely outcome when that probability is 0.1. But now, seeing 1 out of the 5 or 2 out of the 5 have some probabilities that are a little bit further away from 0. And then as I kind of move further right, if the probability of success is 0.1, pretty unlikely I'm going to see all 5 out of the 5 actually be successes, depending on the complexity. And then as I move that probability of success up, well, now the higher number of successes are going to become more likely. So notice same n, right? But now the probability of success is 0.5. It's like flipping a coin. But what are going to be the most likely outcomes? Well, the mean there would be what? 5 times 0.5, so 2.5. So the most likely outcome should be 2 and 3. And then it kind of declines as they move further from that point. But notice as the probability of success went up, these lower number of successes became less likely. The higher number of successes became a little bit more likely. And then let's go even more, right? Keep n the same, but increase the probability to 0.9. Well, now, if the probability of success is really high, then it's likely I'll see like most of these 5 be successes. So now the probability of 4 and 5 have become the most likely. And then seeing a very small number of successes, it's very unlikely that probability is high. Do you have a question?
No.
Okay. So notice here, if I wanted to calculate the mean, 5 times 0.9, 4.5, 4 and 5 are the most likely outcomes. Right? And just because the mean is like 4.5, that doesn't mean 4 and 5 are going to be equally as likely. And I notice 5 is a little bit more likely than 4 there, right? But we know that they'll be the two most likely. We're not saying they're equally likely, but they'll be the most likely. Questions on any of those ideas? So I like that top row. And then as you kind of increase the number of trials, and here I wish I would have kept the probability at 21, but what are you going to do? If you're stealing stuff, I guess, beggars can't be choosers. So here, what would my mean be? Well, 2 times 0.2 is 4. So notice 4, if I calculate and use that binomial function, most likely outcome. And then the probability of seeing fewer number of successes or a higher number of successes declines as I move away from that point. And if the probability of success is relatively low, 0.2, well then seeing like all 20 out of these 20 be successes, very, very unlikely, right? I mean, I'm guessing if you use the binomial function, you can use some of these higher values, you're getting things that are much smaller than 0.02, or 0.002, they're probably out to like 4th or 5th decimal. And then notice as I kind of increase my underlying probability of success, it's almost like it shifts that distribution to the right, right? So notice instead of having this right skewed distribution with a long right tail, if I move that probability of success up a little bit, I'm getting something that looks a little bit more like a normal distribution. In fact, when the probability of success is 0.5, I do have a normal distribution. It's symmetric. Right? As I move the probability of success lower, I get a right skewed distribution. If I move the probability of success to be higher, I get a left skewed. Did I say right there? Right skewed distribution, high probability left skewed distribution. And then notice as we increase the number of trials, we just get a more granular distribution, right? Becomes a little bit, I guess, more interesting to look at. Questions over here? I don't know. I just kind of think there's a nice visualization thinking about as we're I don't know, looking at different examples, thinking about where these probabilities might live. Okay. So just trying to give a few more examples of things we can apply the binomial distribution to. We'll kind of think about these different scenarios and which one would not be appropriate for the binomial. So calculating the number of expected coin flips that come up heads out of 123 flips. Pretty easy. Calculating the probability that at least 5 out of 20 patients get nauseous from the antibiotic. Excuse me, calculating the probability air traffic controllers at the monthly airport make 3 errors per week, or calculating the probability that out of 5 customers in a store, exactly 3 make a purchase. So which of these would not be a very good situation to apply the binomial to? So think about what you would need to apply the binomial. You need a number of trials. You need a probability of success that is the same on every trial, and then you're looking for the probability of seeing a different number of successes. So in the first one, one way to kind of identify your number of trials is, well, what's the highest number of successes I could see? So calculating the number of expected coin flips that come up heads in 123 flips. What's the most heads I could see then? 123. Okay, so I've got an N. The probability of success on any one coin flip is always the same. Pretty good binomial distribution example. What about the kind of patient example, right? What's the highest number of patients I could see get sick from this drug? 20 out of the 20. So I've got an N. Now, you might argue the probability that any one person, depends on the individual, but we're just thinking about, we're looking at the population as a whole, and there's some underlying probability they get sick if they take this drug, we'd have the same probability of success as we administer this to random, 20 different random people. So that's a good one. What about calculating the probability that air traffic controllers make 3 errors this week at one of the airport? Believe it or not, there is an airport in one municipal play. What's the highest number of errors I can see? I don't know. I mean, I guess if it got busy enough, there's probably some technical limit just in the number of minutes that are in a day, or I don't really have a cap. I'm looking for the number of successes over a time period. So we can't apply the binomial in these situations. In fact, the next discrete random variable we'll talk about today And I don't think we'll finish all the examples. We'll probably finish it up on Monday. I'm gonna do continuous distribution on Monday as well. Was the Poisson, well, that's when we want to find the probability of a certain number of successes over a time period. And that means, so that one doesn't apply to the binomial, the last one has to, right? It's the highest number of customers I can see make a purchase out of 5. All 5. I know that when someone walks into a store, there's some underlying probability that they purchase something. Any questions on that idea? Just kind of discussing more of these, thinking about how we identify binomials. So I want to show you how to do this a little bit in Excel, but and it's pretty easy, and it should be the last part of that Excel assignment, which if I recall is due next Wednesday. Hopefully you've already kind of started working on that.
The Excel or the?
Excel, I think is due Wednesday, Connect is due Monday at the end of the day. Am I getting that right? Okay. I might remember these things wrong, so but I believe that's what it was. So one thing that I want to show you before we get to that Excel is let's use the this antibiotic example. Let's say the probability that someone gets sick taking this antibiotic is, I don't know, 0.2, just for the sake of having. My n is going to be 20, and let's say I don't have an x yet. Let's say I want to know what's the probability that at least one person gets sick. Like maybe I'm the company who's administering this, or the hospital. I'm worried about getting sued, right? So I want to, well, what's the probability that I'm going to get at least one person who gets sick and might sue me? So I really want to know what's the probability that at least one person gets nauseous taking this drug. Okay. I know that on average, how many people will get sick? What would my mean be here? Yeah, so we do n times p, not quite 2. So I've got 0.2 as my probability. 20 times 0.2 should be 4. So out of 20 people, I should expect about 4 people get sick. That's going to be the most likely outcome. So it actually kind of matches up with this visual we have here. So if this is the distribution that we have, 4 is the most likely outcome. If I want the probability x is greater than or equal to 1, what would I have to do? So with a student example, I'll look at the range of values I'm looking at, and I'll have to take the probability of x being equal to 1, plus the probability x is equal to 2, plus the probability x is equal to 3. So I'm really adding up all these probabilities. So what should this be pretty close to? 1, right? I'm taking literally every outcome here except for what? 0, right? So it should be, I'm gonna guess, just go out on a limb guess, it's gonna be above 0.9. Right? That'd be a very safe guess, right? I could probably say it might even be greater than 0.99. I don't know. So I'd have to use that binomial function 20 different times. First time plug x is equal to 1, calculate that probability, write it down. Plug in x is equal to 2, calculate that probability, write it down. If I ask you to do this on the exam, it's going to take a lot of time. But I could ask you this on the exam. So what's something maybe I could do to solve for this probability? If I think about this is my event A. So if I want the probability x is greater than or equal to 1, I said the only outcome that isn't in that range is 0.
Did you do 1 minus the probability?
Yeah, right. I know that I can find the probability of an event by taking 1 minus its complement. What's the complement of what I'm looking at? Well, I kind of already said this, but technically it's x is less than 1. But if we're dealing with a discrete random variable, what's the only x value that fits this criteria? X being equal to 0. Now I only have to use that binomial function 1 time, plug in x is equal to 0. Once I get that probability, subtract it from 1, and I'm done. Right? So using that complement rule can make something that seems like very daunting and impossible, especially given the limited amount of time, very doable. In fact, when x is equal to 0, we go back to that binomial function, a lot of stuff starts canceling, right? Because, there we go. If I'm plugging x is 0, 0 factorial is 1, so I can ignore that. I'm gonna have n minus 0, so it's just gonna be n factorial divided by n factorial, I can ignore that. Any probability to the 0 power is gonna be 1, ignore that. 1 minus p n minus x, well, that would be the only thing that I'm really left with that I have to calculate. Right? So that would be pretty easy, actually, if I asked you to do that in the example. Okay. Any questions over that before we kind of jump into Excel here? All right, so I'll probably go through this pretty quick. It's really just a way for you not have to use. You need to put a different chair. That chair doesn't go up very high. So this is just a way for you not to have to use that binomial function. It's already kind of built in. If I can get this to work into Excel. Yeah.
Is any part of our test on?
No. So I won't quiz you like on functions, or I won't ask you like how you would enter in certain functions or anything like that. Okay. And I don't know why this won't let me. Oh, I know why. Got the stupid mouse in here. Okay, so I just have a blank Excel file opened. Okay. I can't remember. I think the example that I give was probably like Detroit home foreclosures. Let me see. Yeah, so oh no, I changed it. So let's say in 2018, 6.7% of the population was considered millionaires. So these are mostly old people who have amassed pretty large wealth. We'll do 0.067. Okay. So our underlying probability of success is 0.067. If I then kind of sample 100 people at random, so I'm looking at 100 people, and let me make sure that matches up. Yeah, I'm doing 100 people here. I could find the probability that a different number of them, like out of the 100, are millionaires, right? So on average, how many would I expect, right? If I think about the mean of this binomially distributed variable, I could just take what? The number of trials, or the 100 people that I'm sampling or asking, times the underlying probability of success, and that should give me the mean. Now, it's kind of with 100 people, it's easy to envision, 6.7 is going to be the mean there. So the most likely outcome I would see is that if I selected 100 people at random across the US, 6 or 7 of them, right, would be considered millionaires, right? So relatively high probability there. Also, I don't think that's actually the right. I looked it up. I think it's actually a lot higher than you'd think, just because of, like I said, asset value, and when you get older, like you kind of need to have like $1 million to retire. So there's, which sounds crazy, but is in reality true if you want to retire at 65. So it's actually a lot higher than you think. I think it is rough. It's going to be somewhere around here. Okay. So the next thing that we might want to do is, okay, what's the probability that, let's do x is equal to 8 first, right? I know that should be a relatively high probability because it's pretty close to that mean, right? But I want to know what the actual probability is. Right? So the binomial distribution function that's built into Excel, right, is just binom.dist. Well, it needs 3 things. Well, actually, technically it needs 4, but it needs the same 3 things that we would have used to plug into that binomial distribution, right? We needed n, x, and p, right? So here, I first need to tell it the number of successes I'm interested in. Well, I kind of forgot to put this in a cell, so I could just type 8 in here. But what I'm going to actually do is select this cell up here, and then I'm going to put in the value of 8 there in just a second. Okay? So right now it's just a placeholder. This is going to be not really, it's going to give me an error because I don't have a value in there yet, but that's where we're going to put x eventually. Okay? The second thing I need to tell it is the number of trials. So x is the first thing I tell it, n is the second thing. So I'll click on that cell. Okay? So if I'm thinking about, maybe to make this a little bit easier than what Excel is telling me, this is really how I need to enter things into Excel. There's 4 things. So x, or the number of successes, n, the number of trials, comma, p, the underlying probability of success in any one trial. And then this very last thing right, is do I want to make this cumulative or not? So if you want to find the probability of exactly one number of successes, it's not cumulative, right? So you'll tell Excel 0. Okay. Talk about what it looks like if we use that cumulative option in a second, but for now, if we just want to find the probability of any one specific value, we'll just use that X is equal to 0. Okay. So I'm going to hit enter. It's going to give me something, but it's screwed up because I haven't really put in my value for X yet. So I go back up here, type in 8. Because I use that cell reference, really what it's doing since it was blank was treating it like 0. So what's the probability we see 0 out of 100 people be millionaires? Probably that I see 8 is around 0.12. And then I can really just play around with that. You know, if I wanted to find the probability that 20 of the 100, well, you get some weird thing here. I don't know if I've addressed this yet, but if I see e to the negative 6, that means move that decimal 6 places to the left. So that's going to be what, 0.00006. So pretty small, right? But you know, I could make that really whatever value I want if I've used that cell reference, and I don't have to worry about typing that binomial distribution function out again in Excel. Okay. Questions on that? Pretty easy. So I'll show you something that's kind of interesting, and then I'll show you how to use the cumulative option. So let's say I go 0, 1, 2, and I'm thinking these are my different values for X. If I left click and drag down, there's a fill series option, right? And then notice it kind of defaults to just increasing by 1. Okay. So I did more than I needed to here. I just wanted to have a bunch of different X values because now notice what could I do? I could use that binomial distribution function. Now I've, So sorry, I might have accidentally said this wrong. I right click, not left click, right? So if you left click, it copies it. If you right click and then go to fill series, all right, then that should work. Did you get it? Yeah. Sorry if I said left click the first time. I might have said it backwards. So if I then want to find the probability that X is equal to these different values for X, right? This random variable X is equal to these different outcomes that I could see, I'll use that binomial distribution function. First thing I tell it is the number of successes I'm interested in, comma, the number of trials, comma, the underlying probability of success. And then we said, we'll make that 0 because we're finding the probability of exactly one value. It's not human. So if I drag this down, how could I very quickly find, instead of typing this out time over time, how could I use this to find the probability of all of them? Yeah, so I'm going to freeze. Yeah, so what am I going to freeze there? Yep, my number of trials and my probability of success, those are not changing, right? The only thing changing when I'm looking at different number of successes is that I'm interested in finding a different probability of a different number of successes. So I'm going to do what? Command T or F4, get those $signs in there. Now, if I double left click here, instead of even dragging this down, it'll automatically copy that down to the very last kind of X value I had. And now I could drag this all the way down to 100 if I wanted to. It's not very interesting because notice once we get to like 20, these are basically 0. I mean, move the decimal point 7 places to the left. We're talking about 0 values there, right? And notice, what are the 2 most likely outcomes here? 6 and 7, the values that are on either side of the mean, and the probabilities as I go in either direction then start to decline. Okay. Questions on this? So this is really practical because I mean companies and things like if I'm worried about like the number of people who are going to default on their loans out of however many customers that I have, or really that you're playing around with like worst case scenarios, right? Like I might want to plan for like how many of these loans will default, or I might want to plan for how many of my my workers either quit or they don't. How many workers am I going to lose in the next month? right? Or all these kind of different, there's plenty of different examples where you can think about, I might want to make projections for the future. Because if I know that it's fairly likely 6 or 7 of my employees leave, well, then I may want to have a plan for that, right? Or 6 out of 7, people default in their loan. I want to make sure I can address that situation if that occurs. Any questions on this before we keep going here? So get one more thing I'll show you, which is, whoops. What if I wanted the probability X is, I'm going to get lazy here, less than or equal to 8, okay? So here, I'm going to use that binomial distribution function again, but now I'm essentially, when I tell it X, if I want this to be cumulative, I guess I'm kind of doing it this way. So whatever X value I tell it, it's essentially going to start there, right? So it's going to find the probability of 8 and then add that to the probability of 7 plus the probability of 6 plus the probability of 5 all the way down to 0, right? So it's going to start at whatever X value you tell it, 8, and then go all the way down, add up all those probabilities. So start at 8, here's my number of trials, here's my probability of success, but then this last thing, I'll put a 1 telling Excel, I want to make this cumulative. Right? I want you not to find the probability of 8, I want you to find the probability of 8, and then add to that the probability of seeing any number of successes below that as well. Okay. So if I hit enter here, I should get a pretty high number, right? Because my most likely outcomes are included in that range. And then the kind of values that are a little bit, less likely, but still pretty likely are also in that range. Now, hopefully, if they've got this coded correct, I could also kind of check this, right? So really all I'm doing when I find the probability that X is less than or equal to 8, I'm taking the probability of 8, plus the probability of 7, plus the probability of 6, all the way down to 0. So I could use, remember what function to add things quick? Yeah, just the sum function. Select these, all right? And hopefully I get the exact same value. Sure enough, I do. Questions on this? Now there's one thing we got to be careful of. So first of all, what if I wanted the probability X is greater than 8? My binomial function doesn't work in the other direction. It only looks at cumulative. It only looks at the probability of seeing a certain X value or anything below it. But if I wanted the probability of being above a certain value, what could I do? I use that complement rule, right? If the probability that X is less than or equal to 8 is 0.77, what's the probability it's greater than? 1 minus that, right? So I can't use that binomial distribution function directly to get the probability of being greater than 8, but I can use it to find the probability that it's less than or equal to that value. And then I know I can just, oops, I forgot something, didn't I? My equal sign, right? I could just do 1 minus that. Okay. Questions? There's one other thing that's a little tricky that I'll be kind and kind of show you. Okay? So what if I want the probability X is less than, let's just do an easy one. We'll do less than 3. Okay. I did. Happy accident. What's Bob Ross say? Happy accidents or something like that. So here I'll put the X value. I'll just type it in to kind of show you. In practice, we might want to use a cell reference so that we could change it. But if I do this, so I'm like, oh, okay, this is easy enough. I want the probability it's less than 3. So number of successes is 3. Number of trials, probability of success, make it cumulative, right? So I enter that in there. It's going to find the probability that it's less than 3, right? But this actually is wrong, right? So why does this not represent the probability that X is less than 3? Yeah, it includes 3, right? Whatever X value I tell that binom.dist function, when I make it cumulative, it starts with that value. So if I want the probability of just being less than a certain value, what do I actually need to do? Well, what's the first outcome that would be less than 3? It's discrete, so 2. Now that's the correct answer. Okay? So you have to be a little bit careful using that binomial dysfunction when you don't have the equality on there, because you don't just take that value, right? You're not starting with that value. You're actually starting with the first outcome that's below that.
We're always gonna have something, we're always gonna deal with it being discrete.
Yeah, for up, so we will Monday talk about the continuous distribution, which is, or sorry, the uniform distribution, which is continuous. But for the binomial, always discrete. Yep. Okay. Any other questions in Excel? Otherwise, I'll kind of introduce kind of the next discrete random variable. Shouldn't be too tough. It's a slightly different formula, but we'll kind of at least introduce the idea. So I think I may not have put the lecture slides don't have this. I wasn't sure how quickly we get through things, but I think we'll be okay. So I'll kind of give you the setup, maybe work through an example or two. We'll touch on this, some different things we can do with the Poisson on Monday, and then we'll kind of do the continuous distribution Monday as well. So I mentioned this a little bit earlier, but that Muncie Airport example was like, well, what if I want to know the number of successes, not out of a certain number of trials, but over a given period of time, right? So kind of think about a setup right here is we've got some event that could occur, and we've got a certain time, like or space, right? So I'll kind of set all the examples up with time. On Monday, I'll show you an example. If it wasn't time, you can do like over a mile, right? Or over some volume of liquid. But for all the examples I give you on the exam, I'll kind of generally keep this as just time. And that's the most common use of the Poisson. So we've got some interval, some time interval. And we know that there's some average that usually happens, or some average number of successes that we usually see over this time interval. Don't worry too much when we're talking about then, okay, what's the probability that, for instance, if there's 5 accidents on a galleon every week, well, what's the probability next week I see 7? Well, I've got a period of time, right, a week. I'm looking at the number of successes, not really successful, the thing I'm looking for, right? The number of accidents on that road. Well, I usually know that there's 5, and I'm looking for the probability that there's 8 this time. So we've got some average that occurs over this interval. Now, we're thinking here, we wouldn't want like our weeks to overlap if we were trying to make predictions like for the whole year. We can't have our time intervals overlap, because maybe the weekends there's more likely to be accidents than others, and so then if the weekends counted in both time periods. But I'll never give you an example where like I'm going to violate that assumption, right? And we generally don't have to worry about that too much, but just to be precise. Okay? So what we really want to know is still the same thing as we did with the binomial. We want to know what's the probability we see this random variable x, or the number of successes we see over this time interval, be equal to different values. I know I could see 0 car accidents on the gallery. I know I could see 1, I could see 2, right? And I can find the probability of all those different outcomes. So it's really the same kind of setup. It's just we can't use the binomial function to give us these probabilities. The function that we're actually going to need looks something like this. Okay? So it's actually much easier than using the binomial. X is still the number of successes we're interested in finding the probability of. Lambda, so this is, as I'm calling this, maybe lambda, I think that's how it's spelled, is going to be the average number of successes that we typically see over this time interval. So we're going to have to be given lambda. Okay, so you'll be told what the average number of successes is over that time interval, and you want to know what's the probability that you see that versus number of successes you're interested in. Now, the only other thing that we might not recognize in this function, because we've already talked about factorials, is this kind of, right? So most calculators, I say most, even like dollar store calculators, likely have this E button, right? So it's just a natural number. It's kind of like pi, right? It's like 2.7, 1828, 1828, keeps on going, right? It's gotten like I don't even know how many, I don't think it's an infinite number of decimals like pi, but it's something insanely large, right? Now, you can't find it on your calculator or something like that, like you could really probably just take it out to that fifth decimal. I feel like I think the way you're supposed to remember is like Abraham Lincoln was 27 or something when he got into politics, and 1828 was the year of some important Abraham Lincoln thing, and there's like, you can memorize it out like 30 places with Abraham Lincoln facts. But I don't remember all of them. At one point, I think someone showed it to me, and I could go out to like 20 some, but that was a long time ago. So, but yeah, that's the only other thing that we need, right? So that's just going to be a constant number. So we really only have two things now. It's easier than the binomial. All right, we've got two things that we're looking at. So I'll go through a quick example. So this guy kind of wrote about the Poisson distribution, also wrote this book of the law of small numbers, which is a book, The Law of Large Numbers, really influential in math. You guys probably don't care. So what he kind of set up was that he was noticing in the Prussian and German cavalry at the time that on average, when he was looking at the historical data, right, that he saw that 0.61 soldiers die every year by horse. Right? You know, so not every year did someone die. Some years maybe multiple people died. He's looking over like the last 50 years, something like that. So you know the average rate over this time period of a year, and then maybe you want to make the projection of, okay, well, what's the probability that I see exactly 3 people die this following year? Right? I don't know why I'd be interested in knowing that exact number, but maybe if I get the, if 3 soldiers die, maybe the loss, the lawsuits or something, or the families will get too upset, and I'll have some negative ramifications. So that's the probability that we're looking for. That X is exactly equal to 3. All I have to do here is I go back. I'll take lambda 0.61. I'll raise it to the X. Our X was 3. E to the negative lambda, then divided by X factorial. And once again, I would try to find that factorial button on your calculator just to make your life a little bit easier, but also this is pretty easy to just enter in as 3 times 2 times 1. Now, also make sure you don't forget when you're taking e to the power on your calculators, it usually is to a positive power. So we're actually taking it to the negative value. So make sure you include that negative sign in there when you're raising e to the power of whatever that lambda is. Okay. So if we plug that in, we can kind of think about, we get a relatively low probability, right? If on average only 0.61 people are dying, it's probably going to be pretty unlikely that 3 people die this next year. Any questions on this idea? What I want to end on. So I think I'm going to skip ahead and then we'll come back to this example next class. So I just want to show you this because it's really easy. We don't have to waste time with it on Monday. If I know the average rate I usually see over this time period is lambda, well, then what's the mean or the expected value over that same time interval? It's just lambda, right? So here, we don't ever have to really calculate the mean, it's given to us. Like we would need to know the mean just to be able to use the Poisson distribution. Now, same kind of idea, so like with a binomial, a regular discrete random variable, we would find the mean like this, then to find the variance, you take first X value minus the mean, whatever, square it, add them all up. If you write that out and you have the function, well, I don't have the general form of the function now, but if you have the function for Poisson distribution right here, everything will simplify down to, and this is a really nice property of the Poisson that people sometimes exploit, which is that the mean is the same as the variance. It's a really weird outcome, but if you do truly have a Poisson distribution, the mean and the variance end up being exactly the same thing, which is just that average rate you typically see over this time period. And then the standard deviation square root of that. Questions? We'll get out of here today. So we'll finish up. We'll do a couple more Poisson distribution examples. We'll also think about what happens if we change the time interval that we're looking for. And then we'll start the continuous distribution. If we don't quite finish it, I'll finish it up at the very beginning of class on Wednesday before we kind of work into exam review. Okay? I would highly suggest start looking at those practice exams, if not over the weekend, early next week. But try to get those homeworks kind of completed so you can kind of move on and start studying for that exam, which will be in class next Friday, a week from today. Okay?
You have like all your time in order to get some.
So it'll